Hello, 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 and welcome back to Shiksha Costa. Today we're going to compare exponential, quadratic, and linear functions. As part of this lesson, we're going to learn how to tell those three functions apart, and you're successful when you can actually do that, when you can distinguish them by making comparisons in all sorts of different ways, hopefully within the same context. And this lesson is actually quite simple. Linear relations, we know the equation looks like mx plus b, that's slope-intercept form. For quadratics, the equation is always ax squared plus bx plus c. And for exponentials, this is a times b to the power of x. An easy way to tell from the table of values, though, is for linear relations, when you subtract consecutive y values, this is called finding the first difference, these are always going to be constant. If this is true, as the x values are constantly increasing, the y values are also constantly increasing. In other words, if this has common first differences, this would be a linear relation. For a quadratic relation, such as this one, for example, the first differences are not constant. But if you subtract those, this is the reason we call these the second differences, we find that those are common or constant. For exponential functions, however, neither of these will be true. An exponential function happens when you are multiplying by the same number again and again and again, and therefore what we say is the first ratios are constant. When we are going from one y value to the next one, you always should be multiplying by the same number. So we say these are common first ratios because the ratio would be 6 over 3, which is equal to 2. 12 over 6, which is also equal to 2. In linear relations, the first difference is tell you exactly what the slope of that linear relation is, and that points you directly to this value here, the coefficient of x. Quadratics don't really have something similar, but for exponentials, the first ratios tell you exactly what the base is. The other part that you can pick out quite easily is the y-intercept. The y-intercept for linear relations is just the constant at the end, and that's true also for quadratics. For exponentials, because there is no constant at the end, instead there is a constant that we are multiplying by, that ends up being the y-intercept. Because when x is 0, b to the power of 0 would just be 1. And 1 times a is just a. And that's it. You can tell an exponential function from a linear or quadratic in a few different ways. Linear functions have a common first difference, quadratics have a common second difference, and exponentials have common first ratios. The equation of a linear function is mx plus b. For quadratic, it's ax squared plus bx plus c. Notice there is an x as a base, and the power of x is 2, no higher than 2. For linear equations, you could say something kind of similar, except x has a power of 1. For exponential functions, though, the way you can tell from its equation is if the exponent has the independent variable, not the base. Its graphs are also quite easy to tell. Linear equations, the word line is right in there. They create perfectly straight lines. The word quadratum from Latin means square, and that's why this is x squared. But the shape of a parabola's graph is, of a quadratic's graph is called a parabola, and it looks kind of like this or like this. For exponential graphs, though, they are really flat on one side, and they rise quite steeply on the other side. In this example, we're going to determine whether this table of values represents an exponential function or not. And I can tell you right now that it does, because to get from 2.5 to 5.25, we have to multiply by 2.1. And that's not an easy number to guess. So how did I come up with this number? It's quite simple. First, ratios tell me that I have to divide. A ratio is like a fraction, two consecutive y values. So 5.25 divided by 2.5 is exactly 2.1. And if I want to check that this is exponential, this first ratio has to be constant for every consecutive y value. And in fact, it is. If I divide 11.025 by this number, 5.25, I get 2.1. If I divide these two, I also get 2.1. If I divide these two, I could take this number and multiply it by this to see if I get this number. That would work too. But I can also just divide them to make sure that the ratio is still 2.1. So because the first ratios are constant, this represents an exponential relation. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.